Welcome to part 2. I'm going to prove that when big F is defined to be this integral, then big F prime is equal to little f, which means that I'm going to show that this thing is less than epsilon. And the first thing I'm going to do is I'm going to show some scratch work, and I'm going to show that I can simplify the numerator here. And the way I can do that is, maybe just down here, I'll draw a little picture. So here's my z naught. Here's my z that I care about, and here is maybe z plus delta z. I'm going to draw 3 paths. Right, so here might be, I might call this gamma. I might call this thing gamma prime. Those are the gammas I use to compute big F. So I integrate along gamma, the red one, to figure out big F of z. I integrate over the green one, gamma prime, to figure out big F of z plus delta z, because that's how it's defined. And then I'm going to have another path, which is just going to be a straight line. I'm going to try that again, straight line. I'm going to try that again, a straight line. That's about as best as I can hope for. That I'll call little l for line. And it goes from z to z plus delta z. And I'm going to do some quick calculations. I'm going to show that we can actually rewrite the numerator as just the integral along L, basically. So this will be scratch work. I'll delete this in just a second. So the integral along gamma plus L minus gamma prime, that creates an integral that goes in a circle around, now minus gamma prime means to go that way. That creates an integral around this enclosed region. It's a closed circle, or it's a closed curve, and f is holomorphic. So the integral of f here is equal to 0 by Cauchy's theorem again. This is also equal to the integral of gamma of f plus the integral around L of f minus the integral around gamma prime of f. Oh, but that gives me 0 is equal to, this is big F of z, this is the integral around L of f, and that is big F of z plus delta z. So in other words, if I move these two big F's on the other side, I get big F of z plus delta z minus big F of z. It's just the integral along, this should be an L, along this green line here. So what I can do is I can replace the numerator here with just a simple integral. The integral along the line of f over delta z minus f of z. Good, that's simpler. We'll see that that's simpler. But actually I want to add one more thing. I want to make sure that I'm clear with the variables, because z is going to be fixed. So I'm going to say the integral around L of f of w dw. So basically all the points along here are w, and I'm just going to add them all up. Okay, I'm going to pause and erase, and then we'll move on. Alright, we're back, and you probably didn't even miss me. So let me rewrite this nicely. Right, I get numerator here is the integral along L of f of w dw all over delta z, which is that length right there, minus, well, I can get a common denominator. Delta z times f of z over delta z. And that's equal to, well, here's what I can do. This bit here, this is the length delta z, which is exactly the length of the blue there, and f of z is a constant, because that's just the value at that particular point. So I can rewrite this as the integral along L, since it has length delta z, of f of z, which is a constant along the line, because this is a z, and I'm going to integrate over w. So these are the w's. That z is just that one point there. So that gives me 2 integrals along the numerator, and that's going to allow me to rewrite this as equals the integral, absolute value of the integral along L of f of w minus f of z dw all over delta z. Okay, stay tuned for the third part of the screencast, which I think might be the last one. Bye-bye.